Hello, this is Paul from Tech. In this lecture, we're going to discuss an important topic called continuity. So we're going to determine the continuity of piecewise function first. And I will going to give you a lot of concepts. Okay, so a lot of, please pay attention. What is a continuity? So we have a definition. This definition is algebraic definition. And later I will give you geometric meaning. Okay, we say f is continuous at x equals a number. Okay, and we need to make sure these three conditions are satisfied at the same time. So the first, we need to define the function at a, which means a should be on the domain of the function. The second is the limit exists. What does the limit exist? Limit, which means the left-hand limit should be equal to right-hand limit, right? Therefore, the limit exists. The third, the existed limit should be equal to the value of the function at a. Okay, 1, 2, 3, all satisfied. We say f is continuous at x equals a. What does it really mean? We need to look at a graph. Okay, we need to look at a graph of the function. Can we look at this function? Okay, we say this function is continuous at a. Why? We're going to verify 1, 2, and 3. So the first, does a functions f defined at a? Yes, because can you see the solid point? And the function is defined at a, which means fa is a value, we know. The second, does the limit exist? Yes. Okay, why? Because the left limit, when x approaches a, the left limit equals the right limit equals fa, right? Good. The limit exists. Does the third, the existed limit equals fa, the value of the function? Yes. Can you see? The limit approaches f at a approaches the value of the function. Okay, definitely this is continuous. What is the real meaning and the geometric? This is exactly the same word. Says the point on the graph approaches this point. Or we say no gap on the curve because this point or the other points approach. Why is other point? Okay, we look at it. If I pick x at here, so the point is here, right? If x approach a, the point will get close and close and close to this point. That means this point is approach this point. That's from the left side. If we look at the right side, because the limit exists the right side. If x is at here, okay, so the point is at there. And then x approach a from the right side, the point on the graph should be approached. Can you see this? Okay, and it gets closer to this point. We say it like this. Or no matter it's from the left or from the right, all the points on the graph will approach this point. This point exactly does AFA, which means we don't have any gap on this graph. Just link all the points together. Continuous, which means no gap. That's the major one. Continuous means no gap. Okay, all smooth, link together. So, what does discontinuity mean? Of course, this is the opposite, right? Okay, so we say f is discontinuous. Okay, of course, is 1, 2, or 3. So either the function is not defined, and we see a gap, or the limit does not exist, or you also see a gap, or even the limit exists, but the limit does not equal the value of the function at a, which means the limit not approach to that point. Okay, that point jump to another way. Okay, so discontinuity, just the opposite of continuity. Let me look at the graph also. So we have 1, 2, 3 example to tell us discontinuous. And the function discontinuous at x equals 1. Why? Because the first, f1 is undefined, right? Can you see the empty circle? The second, the second is discontinuous. Why? Because we see a gap, right, or how do you say gap? Because the left limit does not equal the right limit. The limit does not exist. This is the one, right? Limit does not exist. So this is discontinuous. How about the third example? The function f is discontinuous at x equals 5. Why? Because see, the left limit equal the right, the limit exists. However, the limit does not equal to the value of the function. The value of function jump to there, which means that the third it does not satisfy, right? Okay, no matter is example 1 or example 2 or example 3, can you see? We all see a gap. This is empty. There's a gap. Okay, so gap means what? Okay, if you draw a line, you cannot go smoothly from left to right. You have to jump. You have lift off your pen. Okay, the second is a jump, right? Is a gap, big gap. Here is also a gap. So there is a gap on curve, which means discontinuity. Okay, let me see here. So all the types of discontinuity. We have 3 types we need to discuss. That's important. Okay, and we have removable, or you say is removable discontinuity, infinite discontinuity, or jump discontinuity. All the discontinuous point belongs to any of these 3. Okay, so the first 2 example, what is removable? So here is removable. Here is also removable. Can you see what does it mean? It means if we change the definition at one point, at the point of x equals 2, change the definition. Of course, here the first example we never define. So we define the value of the function at x equals 2 is just here. We fill this hole, and the function gets continuous. Okay, this we call the removable. The second also called removable, which means if we change the definition of the function at x equals 2, we move this point to fill this hole. Okay, so this is going to continuous. Change one point the definition, so the function goes to continuous. We call the removable. First 2 removable. Look at the second 2. The third one, this we call the infinite discontinuity. Okay, the function discontinuous at x equals 0. Okay, why? Because the left limit, the right limit, can you see, goes to the infinity. Okay, the limit that goes to infinity, of course, does not exist, belongs to right. This type of does not exist, or divergence. Okay, diverge to infinity, we call the infinite discontinuity. The last is called jump. This is step function, everyone know. The left limit does not equal the right limit, right? This time. So also the limit does not exist. However, the left limit, the right limit exists, but it does not equal to each other. This time we can find a jump. Okay, the left limit does not equal the right limit, therefore we have to jump, jump, jump. Simply we can call this step function, this jump type. So we summarize. So all this, the first 2 is removable. For removable, all the limit exists, right? But the limit exists for the first 2, we call it removable. The second 2, okay, limit does not exist, limit does not exist. This is a diverge called infinity. This is not a diverge, but the left limit does not equal the right limit, we call it jump. Okay, so all the 3 types. So now we will link the continuity to one-sided continuity. What is one-sided continuity? Do you remember when we define limit, we definitely have defined a one-sided limit, right? Left-handed limit, right-handed limit. So when we define continuity, we also have left-handed limit. This we usually not call the left-handed limit. Okay, so this we call the one-sided continuity. Okay, but it's similar with the one-sided limit. What is one-sided? What is f is continuous from the left at x equals a. Is only look at the left side of the function at x equals a. Okay, to the left of x equals a. how do you say, and this dr 1 2 3 all different is change the limit to the left hand limit because we focus on the graph on the left side of A. Okay, this is the definition. 1 2 3 type. We define, we can find that the left-handed limit equals the value of the function. Let me give you an example. What does the f is continuous from the left? Here it is. And this function is continuous at x equals a from the left. Okay, from the left. But you know this function definitely is jump, right? It's discontinuous at a, however, it's continuous from the left. Why is it continuous from the left? Do you remember? Okay, if I pick A, x from the left side, and when x approach A, can you look at the graph, the point? The point will get closer and closer. Can you see this? The points on the graph will approach this point. This is solid. Okay, and this is empty. Okay, however, we look at the left side is all the solid points. So it is continuous from the left. This is continuous from the left. Let me look at the continuous from the right. A little bit different. Continuous from the right. Okay, so it's the same. We look at is similar. Okay, we only look at the right side of the function at x equals a. Okay, so first is defined the f(a). The second, right-handed limit exists. The right-handed limit equals the value, which means it continues on the right side. Let me give you an example. And here is example for continuous from the right side. So they are the similar function. We just move the value of the function from here to there. Now can you see this is empty and this is solid. This term is continuous from the right. Why? Because when we pick any point x at here, when x approaches from the right side, can you see? Okay, so this point on the graph will get closer and closer to this point. Okay, and they always continuous, right? Always continuous, even going to the end point. This we call the continuous from the right. Is a little bit from a little limit from the left, right? Okay, so this is a limit from continuous from the right. If we put the one-sided limit, one-sided continuity and the original continuity together, we have a result. The result says f is continuous at A should be continuous from the left and continuous from the right. Why? That's definitely true. We should have that. Can you see this example? This function is continuous at A. Does this function continuous from the left at A? Yes. Why? If I pick x here, can we look at it? X, the point is here. If x approach A from the left in the graph, can you see this? Okay, definitely the point will approach this point, right? So, and this function is continuous from the left. The same, also continuous from the right. Why? If x is at here, and if x approach A from the right side, can you look at this point? The point will get closer and closer to this point. Okay, so this function is continuous from the right, right? We can say continuous means continuous from the left and continuous from the right. So what is it? Does not continuous, which means discontinuous. If discontinuous, usually we say this is only continuous from the left, or only continuous from the right, or neither of them. Okay, not continuous from the left, not continuous from the right, also discontinuous. That is the opposite of continuous. And finally, we have one concept. What is continuity on an interval? And we say f the function is continuous on an interval, no matter it's open or end. Okay, so let me look at it. Or close. And f is continuous at every number in the interval. Okay, it's the first. Inside is continuous for all the number. But how about the end points? If the end points, what we can consider is the one-sided continuity. Okay, either continues from the left or continues from the right. For example, f continues at 1 to 5. See, so from the definition, f is continuous at every point in 1 to 5, any point inside the open interval. And how about the 5? This is closed. This closed, it does not continuous, okay, but it is should be continuous from the left, because we defined it on the left side. We did not look at the right. So f is continuous from the left at x equals 5. Okay, continuous inside, and one side the limit continuity on the end point, that is continuity on interval. Okay, that's all the concept. Now I have 2 examples to show how to use this concept to deal with the continuity, or continuous from left, continuous from right. Let me see the first. Okay, how to do? Why the function is discontinuous? Okay, the function is discontinuous at a, which is at 0. The second question, sketch the graph. This is the piecewise function. We know how to sketch the graph. We need to do 2 steps, right? The first prove this is discontinuous. Do you remember? No matter is discontinuous or continuous, we always follow 1, 2, 3 steps. Okay? Do you remember? For continuous, the first is the function should define at a. Have we defined? Yes. The second is the limit exists. We cannot see, but we know how to do calculation. So the second step is going to find the limit. If the limit does not exist, of course it's discontinuous. If the limit exists, we look at the third step. Does the limit equals the value of the function? If the limit also equals the value of the function is continuous, of course it's not, right? This time we need to show is discontinuous. We follow the way 1, 2, 3 always. Okay, the first step, we look at does the function defined at a, which means f, you see, does f at 0 defined? Yes, this time. Why? When x equals 0, y equals 0. So this is 0, right? Which means this is definitely defined. Good. Satisfied for the first. Okay. Satisfied for the first. How about the second condition? Second condition is the limit exists, right? This is the piecewise function. And we need to find the left-handed limit equals the right-handed limit, right? Let me see. We're going to look at the left-handed limit. First, the limit x approaches 0 from the left. Okay, fx. We need to find this first. How to do calculation? We know how to do calculation, right? All we need to do is find the function type. When x approaches 0 from the left, which means less than 0, is a cosine, right? That's a cosine x. How about this? And in the future, I will show you cosine is continuous. Okay, we can do direct substitute, but so far you don't know. However, we do know cosine. We draw a graph. What is cosine? We know the graph of cosine. We look at the pattern. Okay, we look at the graph. We can find the limit from the graph. Of course, when x approaches 0, do you remember is this approaches 1, right? Okay, so this approaches 1. Or you can do direct substitute. Plug this in the future, you will know definitely this is 1. And then we need to look at the left-handed. Okay, so the left-handed we already find. We look at the right-sided or the right-handed limit. Okay, which is this. How to do calculation is the similar. X approaches 0 from the right. And okay, what is f? From the right side of 0. Right side of 0, which means greater than 0. The function is 1 minus. So this time is 1 minus x squared. Okay, this is easy. This is a polynomial. We know directly substitute works, right? Per log 0 into x. So this is 1 minus 0 squared. which is 1. Can we see the left-handed limit equal to the right? So what do we get? So we have this term is the limit when x approaches 0 exists. What is the value? 1. 1 is 1, right? Because 1. And this term is exists. Very good. So this is the second condition. The first satisfied. The second condition limit exists. Now we have to move to the third. Okay, does this limit equals the value of the function? Can you see? This limit equals the value of the function. 1 equals 0. No, 1 does not equal 0. Which means what? The third condition does not satisfy. Which means discontinuous this time. Okay, definitely. Now, what do we get? So the third, we're going to say is this: the limit we just verify when x approaches 0, f x is 1, right? Does not equal to f at 0. F at 0 is 0. They are different. So what? The third one, the third condition does not satisfy. So, and we say f is discontinuous. Is discontinuous. Okay, at x equals 0, we get a conclusion. And I hope you build the experience. All we need to do is verify the first condition, the second condition, and the third condition. Whichever the condition does not satisfy, there is discontinuous. All the three conditions satisfied, that's continuous. Okay. The second, I need to draw the graph, right? So, how do you draw piecewise function? How many pieces this time? X equals 0 is a point, so we cut. So we have the left is less than 0 cosine, one part. The right side is 1 minus x squared, the second part. So we have two pieces. Okay. I will directly going to draw. So first, let me draw the Cartesian system x or y. Okay, so I draw this x. Excuse me. Let me draw y. Okay, so I will draw a vertical line. Whatever. If this is a y, and then I will put a 0. Okay, so I put a 0 here, the origin. We just say, and the graph is cut into two pieces. And what is the cutting point? Cutting point is 0. Okay, so I simply like draw this, or I draw a dotted line. Okay, and this is the cutting line. Left is one piece. Left is y equals cosine. So let me put it here. Y equals cosine x is the left. The right is y equals 1 minus x squared is the right side. So I draw this piece and then draw that piece. Okay. How do you draw cosine? And I know this is like a parabola like that. I only draw one period. Okay, so it's better I get it. Let me draw here. 1, 2, 3, and 4. So here should be negative pi over 2, negative 3 pi over 2, negative 2 pi. Okay, I will draw the graph in one period. So you remember it's a parabola, right? So this is a 1. Jump to 0, down to 0, down to negative 1, then goes up to 0, goes up to 1. Okay, and then I'll link this together like this. Okay, good. It's like a parabola, right? So this is the cosine. Of course, I need to consider how about this point is solid or empty. Be sure. See, when x equals 0, the value is 0. It's not at a cosine x, right? This is not equal 0. So I have to change a little bit. So here I need to put a big empty. So the value of the function go down to here. Okay. So for the boundary point, we should be pay attention. And the last is the right. The right is a parabola. This time it goes down. Okay. The x-intercept is 1, right? So here, so I put a 1 point. So here I put is 1, and then it goes down like this. It just goes down in this way. I roughly draw. Okay, so I put an arrow. So here I also can put an arrow, which means we'll continue. Have you seen this is the basic graph? And the last, can we going to verify is x equals 0 is a discontinuous point? Yeah, definitely. What is the type of the discontinuity? Removable, right? If we change the definition to here, it's continuous. So this type we call the removable. You can see. I'll put it here. Removable discontinuity. Okay, so that's these questions. Now let me show you another question. So here is finding the numbers. Okay, a little bit different. Can we see this question? We read the question first. Find the number at which f is discontinuous. Okay, I will show you where is that kind of point. State that at those points f is continuous from the, because it's discontinuous, probably continuous from the left only, probably continuous from the right only, or none of them. This is the second question. The third question is draw the piecewise function. Okay, I will go into the first. How do you find what kind of point is discontinuous? Okay, we need to do this. Look at the cutting point or the boundary. Okay, how many pieces for this function? 1 piece, 2 piece, 3 piece. For the middle, we have 1 point there, x equals -1. One cutting point, another cutting point is x equals 1. So all the possibility is x equals -1 or x equals 1 are discontinuous. Why? Because inside each piece is a basic function, a continuous. Okay, in the future I will going to show you. So here I list, which means how do you find which point? List the cutting point. That's the possible discontinuous number. Okay, let me show. I will going to show. So the possible discontinuous number or point, which point? X equals -1. Let me show. X equals -1 or x equals 1. X equals 1. Now what do we have to do? We check this one and then check this one by one. Okay, so we check the first. We check x equals -1. We're going to see if this point is discontinuous or continuous. Okay, do you remember how to do? We're going to verify each condition, right? 1, 2, 3. All this is the same. Now we're going to do the same. Look at x equals -1. So the first step is look at f at this point is defined or undefined. This is defined. How many? When x equals -1, is x is -1. This is defined. Okay, so this is easy to look at. Did the first step. Then we go on to the second condition. If the limit exists or not. Now our directory. You remember this function, right? So I will use this function later. Now I will go on to the second step. We look at each limit, each sided limit. Okay, so we look at the x approach -1 from the left. Okay, the left-handed limit first. How to do? All we need is plug into the function. What is the function? When x approach -1 from the left. Put -1 from the left. Left of -1 is x squared. So I put the x squared here. And this is a polynomial, right? Directly substitute. Each is -1 parenthesis square is 1. We find it the first. Now we're going to find the right-handed limit, which is this. X approach -1 from the right side, f(x). Okay, of course, we need to find what is the function? The right side of -1, so is the second piece, which is x, y equals x. So let me put it here. When x is positive, that's the polynomials. They are directly substituted, which is -1, right? Okay. What do we get? We get the left-handed limit does not equal to the right-handed limit. What do we say? We say this. We say the left-handed limit, okay, does not equals the right-handed limit. So the limit does not exist, right? So we have this. The limit when x approaches -1, okay, fx does, I simplify, does not exist. Okay, so can we see? This is the second. The second we already say the limit does not exist, which means what? Which means we don't need to go to the third condition. We already can make a conclusion. What? The limit that does not exist, of course, is discontinuous, right? So I make. So we can say f x is already discontinuous. Is already discontinuous at x equals -1, right? X equals -1. This is the conclusion already. But we need to look at it. State that at those discontinuous point, f is continuous from left or from right or neither. What do you say? Okay, all we need to look at it. If the left limit approach to the value of the function, or the right-handed limit approach to the value of the function. What is the value of the function? The value of the function is -1. Okay, so -1, can we see? The right-handed limit equals -1. So we can say this. And based on the calculation we did, well, I can make this conclusion. And the right-handed limit, when x approaches -1 from the right, fx equals -1 equals the value of the function at -1. The left-handed limit does not equal to. What does this mean? This means approach from the right. Approach from the right. So we can make a conclusion. So we can say f is continuous. Okay, is continuous from the right at x equals -1. If someone you like this continuous is only, okay, it's continuous from the right but not continuous from the left. Okay, that's the first one we checked. Have you see? We checked the x equals -1. Now we follow the same way to check x equals 1. What to do? We check 1, 2, 3, right? We need to check 1, 2, and 3. We're going to check x equals 1. Okay, so this time. So they are the same. The first, we check f1. Does f1 define? Okay, so if we're going to look at f1 defined, f1 is 1 out of 1, right? Defined, definitely. Is 1 out of 1 equals 1 defined. Good. The first we check. And then we check the second. The limit, the same. Of course, because piecewise, we have to look at the left-handed limit and the right-handed. Okay, I'll look at the left-handed first. What is the function beside the left of 1? The left of 1 is the second piece, x, which is x. That's a polynomial. Directly substituted is 1. Okay, now we look at the right-handed limit. What is the function type? Let me see. The right is 1 out of x, so I will put 1 out of x. Okay, it's okay after the parentheses. So here's 1 over 1, right? The quotient rule, 1 over 1. we get 1. Okay, so this time different. What do we get? We get the left hand limit equal to right hand limit, which means what? Which means this special, so we get the left, make a conclusion, the left-handed limit equals the right-handed limit, which means what? Okay, which means the limit x approach 1, f x exists, right? See, we can say the limit exists. So that's the second condition. Now we have to move to the third condition. Does this limit equals to the valued function? Let me see. This limit exists equals what? This limit symbol you say equals 1, right? Can you see this? 1 equals 1. This 1 equals the valued function add 1, which means the third step. So I will going to see the limit x approach 1 f(x) equals the value of the function add 1, both equals 1. Therefore what? The first condition, the second condition, the third condition all satisfied. Therefore we get a conclusion. So f(x) is continuous at x equals 1. Okay, so both of point or number we checked. So we checked x equals 1 continuous, x equals -1 is discontinuous, right? Okay, good. Now all we do, sketch the graph. Okay, sketch the graph, 1 piece, 2 piece, 3 piece. Okay, so already sketched the graph here. So you can see here is the graph I sketched. So you also can sketch the same. The first piece is quadratic. The second piece is linear. The third is reciprocal. Okay, so you cut. This is the cutting line, and draw each piece. Okay, and all you need to do is pay attention to this boundary point. Let me show you. Why here is empty and here is solid? Because can you see? X less than -1. X equals -1, so -1 the point should be goes to the second piece. So here is solid, here is empty. So how about the last? This is of course is going to the third piece, 1 over 1x1. So this point belongs to the third piece. So we have piece 1, piece 2, piece 3. That's the graph. Of course we can verify. Do you remember? We proved that, or we found x equals 1 is continuous. Is this continuous? Yes, no gap. And we also find x equals -1 is discontinuous. Is this discontinuous? Yes, big gap, right? Big gap. What the type of discontinuity? Okay, ask you the last questions. This time is the left-handed limit does not equal to the right-handed limit. Do you remember? That belongs to jump. From here to there, jump. So this is the final. I say is jump, discontinuity. Okay, that's all. Thank you.